Hello everybody. So, but till now our discussions, they were primarily confined to closed systems, right? Closed systems means those systems which have been interacting with the surroundings under different conditions of interest. Maybe say for example, they were interacting with the surroundings under constant volume entropy. They were also interacting under constant PS, they were interacting with under constant TV, and they were interacting under constant TP. But in all the cases, we had kept in mind that we are dealing with closed systems where all the interactions did not concern mass changes of the system due to interaction with the surroundings. Even if there was a chemical reaction inside the system, we ensured that the effect was primarily that of volume change, while the composition and the total mass of the system were kept constant. Now, under that condition, what did we observe? We found out that for that particular condition, we had defined different thermodynamic potentials, or the changes of the different thermodynamic potentials under different conditions of interactions between the system and the surroundings. And the changes between of the different thermodynamic potentials, they were related to changes in other properties. So, when a system moves from one equilibrium state to the other equilibrium state while interacting with the surroundings under different particular conditions, and these were the 4 conditions of interest which we were dealing with, right. Now, suppose and one more thing I would like you to remember, that all the equations which I have written down here, all this set of equations, they are primarily concerned with only PV type of work and or the work of expansion, and no other non-PV work involved. If there is a non-PV work, then definitely we have a plus FDR here, that we have already discussed. We have discussed both the criteria of equilibrium, both for PV type of work as well as for non-PV type of work. Now, this entire thing, this was for the whole thing was suggested for closed systems with only PV work. Now, suppose I try to deal with open systems, when along with energy there is mass transfer between the system and the surroundings. What do you expect under this particular condition when we deal with open systems? Keeping in mind that even for open systems, we shall be dealing with only PV type of work. Now, how have we defined the change of, say, if we take the first equation, how have we defined the change of du with change of S and V? Remember another thing, the equations which I have written down here, they are all for total properties or total extensive properties of the system, and the importance of differentiating between the total and the molar or the mass specific properties will be very clear today itself in this class as I proceed further. Now, in what way have I defined the change of U? I have, for changes in, say, in total entropy and total volume, first I have defined del U del S at constant V times the dV, and then I have defined del U del V at constant S. Now, suppose there is change in the number of moles. Now, for the time being, again I will mention that we are considering only PV type of work and single component systems. These are the 2 things that we are going to consider for the time being. Now, for these cases, what do you expect is which term is going to be added? Here we are going to have one term del U del N under conditions of constant S and V, right, into dN. And moment we add up one more variable, what are we required to do? We are required to write Sn here, we are required to write Vn here. So, therefore, when du changes as a result of change in entropy, total volume and total number of moles of the system, then the differential equation for du comprises of 3 terms. The one term denoting the change of u with S when volume and the total number of moles are constant. The second term dealing with change of U with volume when entropy and total number of moles are constant, and the third term deals with the change of U with N when total entropy and total volume of the system remains constant. The same thing is applicable for each and every equation that we have written down. For example, here we are going to have something like del H del N at constant S and P, and immediately we are supposed to put one N here and one N here. Same thing is going to apply to this case as well, where we are going to write this down, constant T and V, both of them are capital, and we have to write it down in this particular way. Here also we are supposed to write del G del N constant Tp. Here we are going to have a constant N, here we are going to have a constant N, right. So, moment we shift from closed to open systems, we find that initially we had 2 terms, now we are having 3 terms in all the differential equations. Well, so the next question which comes up is, what are these particular terms that we have written down? What is this particular term? What is this particular term? What is this term? And what is this term? Now, just if you look closely at these terms, what is the term? Let me write it down here. It is del U del N at constant SV. So, therefore, it is the change of internal energy with change in the number of moles. So, at the first intuition it appears that this should be the molar internal energy of the system. Let us see if our initial intuition is correct or not, and the same thing should apply to each and every case. For example, del H del N at constant Sp, this possibly then should correspond to small h, this should correspond to small a, and this should correspond to small g. Now, let us see if our supposition is correct or not. What is del U del N at constant capital S capital V? This is equal to U. Now, what is capital U? Capital U is nothing but N times U. So, therefore, what is this particular term? This term is nothing but U plus N del U del N at constant capital S capital V, right. Now, try to understand it very well, since this is the molar property. So, whatever equation I have written down for the total property, the same equation should be applicable for the molar property when this equation is written in terms of molar quantities, right. So, therefore, we know that du, this is equal to Tds minus Pdv. What does it imply? It implies that du at constant molar entropy molar volume is equal to 0. You get my point? So, therefore, if du at molar entropy molar volume is equal to 0, so therefore, and we know capital S is nothing but equal to Ns, we know capital V is equal to Nv. So, therefore, if we are keeping this constant and we are varying this, it is quite natural that this also has to be varied. This cannot be kept constant. The same way, if we are keeping this constant and we want to vary this, then this also has to vary. This cannot be kept constant. So, what I mean to say is, you cannot keep total entropy and molar entropy constant at the same time when the total number of moles of a system are varying. The same thing is true for volume. You cannot keep total volume and molar volume constant at the same time when the number of moles are varying. So, therefore, what I mean is that if your du at small sv equals to 0, then definitely we can write this down as del capital U del N at small sv, this is equal to U, right. And we also can write this down as that del capital N del U for small sv, this cannot be equal to del U del N at capital S capital V, right. because we know that this and this cannot be kept constant at the same time when n is varying. Now, if this equation has to be true, then in that case this term has to vanish. But we find that if this term vanishes, then this term cannot vanish. So, therefore, it automatically implies that this is a non-zero term, as a result of which your del u del n at constant capital S capital V is not equal to the molar internal energy of the system. So, therefore, the first thing which we realized is then this particular term which has been written down, this particular term is not equal to the molar internal energy. So, the next question arises, what is it? Then do we have to define it in terms of some other molar properties? Is that molar property different for each and every differential equation? Then we land up into a set of 4 additional molar properties which are not the true molar properties in that particular sense. So, the next, once it was realized that these quantities, they do not correspond to the molar quantities, at least for the first 3 cases. Let us see for the del G case what we get. For the del G case, again we can write down dg, it is equal to del G del T. I have already written the equation on the overhead slides, yet I would like to repeat it once more. Del G del P at constant T n dp plus del G del n at constant Tp. I repeat again and again the same thing. This equation is applicable only for a single component open system. Now, in this case, for what is G equals to, again proceeding in the similar way, it is equal to Ng. So, therefore, del G del n at constant Tp, it is nothing but equals to Ng del n at constant Tp, which is nothing but equal to G plus n del G del n at constant Tp. Here also I write down the same thing. I can write it down as dg equals to minus s dt plus v dp, right. So, therefore, dg at constant Tp equals to 0. So, therefore, del G del n at constant Tp, this is equal to G. So, therefore, we find that in this particular case, this part del G del dg at constant Tp equals to 0. So, therefore, this part cancels out, and we know del G del n at constant Tp is nothing but equal to the molar Gibbs free energy of the system. So, therefore, what we deduce is that although the previous molar quantities did not correspond, rather the previous quantities, the third terms which I have written down, do not correspond to the molar properties, but del G del n at constant Tp corresponds to the molar Gibbs free energy. Now, let us see what these terms correspond to. I will be doing the derivation just with del u del n at constant Sv, and please note that the same derivation is going to be applicable for this term, same derivation is going to be applicable for this term. I leave it as an home assignment to repeat the derivation which I have done and to find out the corresponding expression for del H del n and del A del n subject to the respective constraints. Let us see what it is. Now, again I repeat, u is nothing but equals to n u, right, this I know. So, therefore, I can write it down as du is nothing but equals to n du plus u dn. I can definitely write it down in this particular way. Now, what is du equals to? Du, several times you must have learned by heart by this time. Write it down in this particular form. So, therefore, this can be written down as T ds minus P dv. Since their properties, I can play with them in any particular way, it hardly matters provided the initial and final states are constant, and I can write it down in this particular way. So therefore this can be written down as NTTS minus NPdV plus UdN, right. Now can I write this particular equation as, I just write it down once more to maintain continuity, NTTS minus NPdV plus UdN, right. Can I write it down as T dNs minus SdN? From Laplace from Legendre transform I can very well do this. Similar way I can also write this down as P dNv minus Vdn plus Udn. Now you look very carefully what I have got. I have got du equals to d of dn of u minus ts plus pv, spu, all of them are small case alphabets, minus ttns minus pdnv. What is this term? This is capital S, this is capital V. So what do I get? I get, and what is this term? U plus PV minus TS, it's nothing but the molar Gibbs free energy. So what do I get? du is nothing but equals to GdN minus TDS, sorry, this is plus TDS minus PdV. So therefore what do I find? That my initial equation which I had written down for closed systems, along with that I need one more term GdN here in order to extend the closed system equation to open systems. If we repeat the derivations for dH, dA, etc., we find that for each case we can incorporate a term GdN and the equation becomes applicable for open systems, and even this GdN term is applicable for the fourth equation as well. So therefore for all the equations I find that for open systems we find that this particular term, it corresponds to the molar Gibbs free energy, and therefore we can write it down as, so therefore we can write it down as del U del N at constant SV, this is equal to del H del N constant SP del A del N at constant TV, this is equal to del G del N at constant TP, which is nothing but equal to G. Now therefore from here it is quite evident that this particular term, the molar Gibbs free energy, that is quite important, and since it is quite important, so therefore this assumes a very important role in phase equilibrium thermodynamics, and it is often called chemical potential of a substance, and where chemical potential of a substance is nothing but its molar isobaric isothermal potential, or it can be its mass specific isobaric isothermal potential. It all depends upon the way we have defined the mole numbers or the mass numbers, right. Now this was for a single component system, and from these particular equations we can arrive at another very important relationship. Let us see this particular relationship which I have written down, this particular relationship. From there we can write it down as du equals to TdS minus PdV plus, since the molar Gibbs free energy is often called the chemical potential. I can define it in terms of chemical potential. Now, again applying Legendre transform, we can write this equation as equals to du plus dPv minus Vdp minus of d of mu n minus n d mu, right. So, again from here we can write d of u plus Pv minus Ts, this will be equal to plus SdT minus Vdp plus n d mu minus d n mu equals to 0, where this we know is nothing but g, this part we know is nothing but g. So, therefore, this part and this part cancels out, giving us a very important equation which is very useful for phase equilibrium thermodynamics, and this particular equation is known as the Gibbs-Duhem equation. What does this particular equation suggest? It tells us that for a single component open system, we cannot vary T, P and mu at the same time. If we fix up mu and P, T automatically gets fixed up, and it is true for all the other systems. So, therefore, all of them cannot be varied at the same time. If one of them or that both of them are varied, the third one automatically gets fixed. Now, this particular equation has got a greater applicability when we go for multi-component open systems, which we will be discussing in the next lecture. Thank you very much.